Hey guys, my name is Kasura, your fellow student, and I've noticed that some people are having difficulties in solving this question, and I thought to like take a bit of my time to help some of you guys to like solve it. So in this situation, they told us to like find the state fidelity of the zero state and the Bell state, like the question here. So there are two methods on how to solve this. The having the first one that we can use the same circuit to solve this problem, and the other one consists of two circuits. So without wasting enough time, let's jump straight to it. To start with, we have to like have our state, our zero zero state, and we need to like store it in a variable. Like for example, let me initialize my state. Okay, I'm now initializing my circuit like so. um my keyboard is like a bit 40, so I'll use the on-screen keyboard to use some other keys which I cannot use on my keyboard. Okay, so to solve this problem we need two qubits. Hence I'll initialize my circuit with two qubits. So these how state fidelity works. State fidelity is actually a Qiskit function which takes two arguments and it compares them to give an output of 0 or 1 or anything in between, considering how the output is compared to each other. So to solve this problem here, I'll first store the 00 state qubit, which I will later on compare to the Bell state to find our state fidelity. So from our instruction, which is about the um, state vector is a function. I mean, yeah, it's a function. So it's going to take in our circuit. Having said this, we have stored the initial state of 00 in a variable called initial vector. The next step now is to um, uh, transition our circuit into a Bell state and storing it into our final state, which we are going to compare with our initial state. So having said that, let me do the coding. um, so qc dot hardamagate to put it in superposition. So we're going to put our zero state into superposition like so. Then to entangle our first qubit to our second qubit, we're going to utilize the uh, C NOT gate, our controlled X gate, which we are going to use our first big qubit has our control and our second qubit has our target. Uh, yes. So I from there we can safely say that we have entangled our circuit. By entanglement, I mean the state we are going to have from the superposition, it being a zero will guarantee us getting a zero in the second qubit. If we get a one in the first qubit, that means we also have a one in our second qubit. So having that, we have transitioned our circuit into a Bell state. We can now store the the state in a variable called the final state, like so, using the method like from above here. Yeah. Okay, having that we have stored our final state, we can now safely compare our initial state and our final state to find the state fidelity. Give our first argument, which is our initial state, and passing our final state separated by a comma, like so. Notice that I made a typo here when defining our initial state, so I just corrected it. Yeah. So having said that, if we are to run this circuit, we are going to have a state fidelity of 0.5. Having that, our first uh, circuit is in the 00 state, and our Bell state can give out a 1 or a 0. So that means uh, we can only agree to our initial state 50% of the time. So if I'm to run this cell here, we are going to like find the state fidelity. Bear with me, I'm using my PC and it's kind of slow, so it might take a little bit of your time. Okay, there you go. We now have the 0 0.5. That's how we find the state fidelity for the first state. I mean, for the first method. For the second method, uh, we are going to define uh, two circuits. One being our 00 state and another one being our Bell state. So without wasting time, let me get to it. So our 0 state, I'll call this our 0 state, then initialize it with 2 qubits. Like so. So I'm now going to store our initial state for the 00 state into a variable called initial. Note we are using the same method we use to store uh, our variable from above. Instruction. Now we're going to get the instruction from our 0 state, like so. So for the second method, we are down at step 1. We have initialized the 00 state circuit, and we have stored our state vector in a variable called initial. So we are now moving on to the second step, which we are going to define our Bell state. So I'll call this circuit Belsted. I'm going to initialize it by the same number of qubits from above, because we need 2 qubits for both situations, like so. Having initialized the Bell state, we are yet to actually make it in a Bell state. We just like stated, say, okay, we want our Bell state to consist of 2 qubits, but we haven't entangled our qubits. To entangle our qubits, we're supposed to introduce the Hardaman gate and the the control C gate. Yes, like from above here. So without wasting time, let me get to it. State vector dot Hardaman. We are going to apply the Hardaman gate on the first qubit. Then we are going to use our first qubit as our control qubit. Then the target will be the second qubit, like so. Having done that, we have initialized our Bell state and we have integrated our qubit. So I'm now going to store them in a variable which I'll decide to call final. Note that you can call these variables whatever. You can call it initial state, as long as you just remember that, oh, you called it that. So even when you are passing it to the state fidelity function, you call the right variable name. Okay, having stored our final state vector, we are now moving on to step 3, which is comparing our initial and final to find the state fidelity. Like I said earlier, the state fidelity actually takes 2 arguments. So in this case, our arguments being the initial and final, like so. So having done this, we can safely say that we have solved the problem above. So if I'm to run this cell, we are to get the same state fidelity like above here, which is 0 0.5, saying that these state vectors agree 50% of the time. Like so. So there you go, guys. As you can see, we have solved the problem, and deciding which method you would use, it's up to you, but the key thing is to get your answer, and that answer is supposed to be correct. So thank you guys for your time, and thank you for watching.